Since my last video, a lot has changed for Jugglebot. I'm pretty sure I've changed just about every single subsystem in Jugglebot, so there's a lot to cover in this video. But before we get into any of the juicy details, I want to show you just what Jugglebot can do now. So making Jugglebot just move straight up, it can throw the ball about 50 centimeters, 60 centimeters up in the air, and with catching, it's not really making any attempt to actually catch properly. It's just sitting there, waiting for the ball to come back, and hopefully the ball lands in the right spot and it goes back down and then can make another throw. But in most cases, that doesn't happen. So I tried having a bit of a play around getting the timing right to get it to move down at the right time so that it would actually receive the ball somewhat correctly. But that was a little bit tricky, and I couldn't get it to throw perfectly straight up every single time. I tried wedging a book underneath one side, which is a little bit cheating, but that didn't really fix it. And after stuffing around with this for like 10 minutes or so, I didn't want to bother continuing with that because it's not really much point to doing that because I'm going to have to make it a lot more robust later anyway. But it got about 3 to 5 catches on its most successful run. So I think that's pretty damn good. And that's throwing to a height at which I can juggle 5 balls. So I guess in theory, if I had 2 of these, with a little bit of software improvement, it should be able to juggle 5 balls, at least. So that's pretty good, and I am very happy with that so far. It is a huge improvement on what was happening in my last video and prior, and now I'm getting closer to a design that is really properly fast enough, and so the hardware is almost at a point where it's solid enough for me to sort of like step back on that and move more to software. For the rest of this video, I want to cover what all of the subsystems in Jugglebot are and how I've changed them since my previous designs. And that will hopefully give you a decent understanding of what's actually going on here. And then at the end of the video, I want to talk about what some of the improvements are going to be that I will make for the next video and moving forward, and why I'm going to do them. There's a few things that are relatively minor in the grand scheme of things that's going to make this perform a lot better. And I'm very keen for that. Working from top down, the first subcomponent that we hit is the hand. And this component has the objective of actually receiving and throwing the ball. It's the only thing that should be contacting the ball ever. By pulling these strings down, the carrier, as I've been calling it, will move the ball up, and if you do that fast enough, it will throw the ball up. Now you might notice that there's no motor here to pull these strings down, and the way that that happens is the rest of the platform instead moves up. So instead of me pulling these strings down away from the rest of the hand, instead the hand moves away from the strings, which is a little bit of a weird way to think about it, but it works. The big changes that I've made to the hand mostly just amount to making it more simplified. I've gotten rid of the arms that were holding onto the linear rods and sliding along them. The tolerances there were not working properly and the linear bearings were not sliding smoothly along the rods. But if you go really slowly, it's very sort of crunchy. So I got rid of them completely, and now the carrier is just free to move around, which shouldn't be a problem in the future. I don't think it will be, but time will tell. The next thing that I've changed is I've made a bit of a modification to what I've been calling the tip cap, because you have to have names for these things because your files have to have names. And that basically just amounts to, again, making it more simple. I got rid of one set of pulleys and instead replaced it with a PTFE guide. So the string just runs through this guide, and it's much easier to make, much easier to deal with because the string can come off of a pulley, but the string can't just come out of the tube. If it's in the tube, it's going to stay in the tube. And that's very, very nice. It was really annoying when the string used to hop off of the pulley and go next to it and get stuck, and I would have to get in there with tweezers and pull it out. That was really frustrating. Then moving down further, I've also changed the way that the strings are tensioned. Because there are 3 strings here, they need to all be the same length. And if they're not the same length, then the carrier will become tilted and the ball will not be thrown straight. And that's not ideal. So I need these 3 strings to be exactly the same length. And I am not trusting myself to tie knots to be exactly the same length. That's just not going to happen. So I need some way to adjust the length of these strings. Previously, in my old design, that adjustment mechanism was inside the carrier of the ball. And that was cool. I think it was a pretty neat design, but it was really hard to make. And it was very frustrating to get all the strings in there and glued in place. And I didn't want to have to do that again after I did it the one time. So I've moved that tensioning mechanism down onto the base now, where it's a very simple mechanism. I can just screw in and screw out these 3 screws, and the length of the strings will change. So I can adjust those to get the lengths to be perfectly correct. And the end result is, in my opinion, a much more simplified hand that is very, very smooth, and it works really, really well. I'm really happy with how that design has improved. Importantly as well, I have kept the aspect of this design that makes it removable from the rest of Jugglebot. A couple of designs ago, I had it so that the hand was not really removable, and so any adjustments that I made to the hand, I basically had to take all of Jugglebot apart, and it was really annoying. But having this be modular, I can just remove the hand out, make any changes that I need to make, and then put it back in, and it works really well. Modularity is something that I've been really trying to move towards with Jugglebot the more I get into this, because it's really nice being able to just chop and change subsystems and not have to worry about the rest of the design. Very nice. The next major subsystem along is the platform, and this consists of these 6 carbon fiber rods and strings connecting them all together. These strings are really important because if they're not there, there's nothing stopping the platform from flexing out. I mean, there is a little bit, there's the stiffness of the carbon fiber rods and the printed parts, but given the geometry of everything, that's not very much. And so without these strings, the whole system is allowed to flex way too much. But with the strings, it's very stiff and the whole system barely flexes at all. The only big change that I've made to the platform since my last design is to change the joints that attaches the platform to the legs. Previously, I was using some ball joints that I just bought online from RS, and they were cool, but they had very limited range of motion, and I had to position them in just the right way to make the most of that limited range of motion. And it was really annoying to do that, and there were a couple times where I forgot to change the angles of them, and I had to reprint parts again and again, and it was just frustrating. I didn't want range of motion of the joints to be the limiting factor of how far Jugglebot can move around, so I just designed my own joints and now have these. And these are really cool in my opinion. They have an enormous range of motion, and now these joints should not be the limiting feature of how far Jugglebot can move around. There is a little bit of slop in their movement, and I could optimize that a little bit better to get the printing tolerances a bit tighter, but as it is now, it's pretty good, and I haven't noticed any major issues with that, so I'm probably not going to change that anytime soon. The next subsystem down are the legs, and these are the system that have by far changed the most out of anything else. These are completely different to what I had before, and for the better, entirely, 100%, they are much better than they were before. These new legs are faster and lighter and quieter, and they're just better. In my opinion, they also look quite a bit nicer, so it's just win, 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 win. It took a little while to land at this design, and my first couple designs were a little bit overcomplicated for what I have to do. There were too many moving parts, too many gears meshing with each other, and they were just, a little bit too complicated. But after working through a couple designs, I landed on this one, and I think it is great for what I need to do. It's surprisingly good at holding the carbon fiber rod in place, and they're super light and very, very responsive. To describe how these new legs work, there's a carbon fiber tube that, by being pulled up and down, will make the leg go longer and shorter. This tube is supported by 6 bearings, here they're shown green, in 2 sets of 3. If you look from above, it's pretty clear that these 6 bearings do a very good job of restricting the motion of this tube so that it can only move up and down. And to give further support to this tube so that it can't wobble from side to side, these 2 sets of 3 bearings are spaced out by about 50 millimeters or so that the tube really can only go straight up and down. To actually pull this tube up, there are strings that go from in this hole here, on the other side of which there's just a knot that's been tied so the string can't pull back through. That string goes up, passes over these black pulleys up the top, passes down through this little manifold part down here, and then ultimately out through the base block and then out to where the motor is. I've designed this to support 3 strings so that they are all sort of like radially symmetric about the tube. But I've found that after doing a bit of testing that only 1 string is necessary, and so I'm only actually using 1 string in the real thing. That describes how the tube gets pulled up, but not how it gets pulled back down again. And that works with 3 constant force springs. I haven't modeled these springs in this model because they're a little bit annoying to model and I don't really need to model them, so they're not here, but you can use your imagination. 2 of these springs are placed in these slots here. So there's one in here and there's one in here. And those just rest on bolts that pass through these holes. And the 3rd spring wraps around this drum here, which I will get to in just a second. To attach these constant force springs onto the carbon fiber tube so that it can actually pull the tube back down again, the constant force springs have little holes punched into the end of them, and those holes meet up with these holes, and a bolt passes through the lot and fixes the spring to this plastic part, allowing it to pull back down again. The reason why the 3rd constant force spring wraps around this drum here is so that I can use a rotary encoder to track the exact position of the leg at all times. The way that this works is with a special magnet called a diametrical magnet placed in the end of this drum, and as that spins around, the chip on the rotary encoder, which is this black square here, can detect that rotation with very fine precision. And so then I can take that reading from the encoder and extrapolate to know exactly how long the leg is at all times. One of the biggest advantages of this design for the legs is that the motors are now not inbuilt into the leg. My last design had the motors very solidly fixed in place, and to get them out basically meant taking apart the entire leg. But with this new design, because the string can be pulled from anywhere as long as it's routed in a relatively frictionless way, the motor can be placed off of the leg and is therefore very easy to access and very easy to change. As it is right now, I have the string routed around and it goes down through the base attachment point of the legs and then out through a little channel to where the motor is attached. You might be thinking that with all of these twists and turns, surely there's a lot of friction in the system, but the PTFE tubes do a really good job of routing the string around, and I'm actually very surprised at how little friction there is in this system. And even with friction, the motors are quite strong, so that's not really that big of an issue right now. You might be wondering why I went to the effort of putting rotary encoders on all the legs so that I know the exact leg position when I'm using stepper motors. Because part of the way that stepper motors work is that unless they stuff up, you always know exactly where they are at all times. And there's 2 reasons for this. The first is that because of the new way that the string is routed around, I'm not expecting the relationship between the motor turning and the leg moving to be perfectly in sync and perfectly linear. There's going to be some slop in this system. This is essentially a Bowden tube system, like what you have on your brake lines or what some 3D printers use. And there's always a little bit of slop in there. It's very hard to get them perfect. So by having that rotary encoder, I can know for sure exactly how long the leg is at any given instant. And the second reason is because I'm going to swap out these stepper motors with some brushless DC motors. I probably should have used brushless DC motors from the very beginning, but when I was going through the process of like speccing the parts for this, I didn't know what I was doing. I'd never used motors before, and I found it very hard to get good information about how strong and how fast brushless DC motors were. These stepper motors that I bought are pretty much the only motors that I could find that had the specifications that I wanted available to me and that weren't ludicrously expensive. So that's pretty much the only reason why I went with these. I have since learned a fair bit more about brushless DC motors and how they work and how to quantify how strong they are. And I'm very confident that once I change these out for some better motors that I've bought, Jugglebot's going to be so much better. It's going to be so much faster. It's going to be a little bit of a learning curve to actually implement those motors in Jugglebot because I've never used brushless DC motors before, but from what I can tell, it's not too tricky and shouldn't take too long. That takes me nicely into what other things I'm going to be changing in the nearish future. The most important is going to be changing these motors for brushless DC motors. I think that's going to be probably the biggest change, but I think the next biggest will be changing the way that the legs are pulled up and down. The first change that I want to make to how the legs work is to change the way that the string is routed that pulls the leg up. Right now, this tube is routed in a kind of clean way, I think. I think it looks quite nice, but it's not really that functional because it restricts the tube from bending and contorting and means that it's under undue stress and it gets pushed and pulled in really weird ways, and it's just not the best. I want to free that up as much as I can so that the tube is only attached where it has to be. And I think by doing that, it will be a lot more free to move around as the leg moves around. The second thing that I want to change is to get rid of these constant force springs that pull the leg back down again. I think it was a cool idea, and I'm glad that I tried it, but there's two big problems with these springs. The first is that they're not fast enough. They don't have enough force to pull the leg back down quickly. They are pretty quick, but they are not as fast pulling the leg down as the motors are pulling the leg up. And right now, they are a pretty significant limiting feature of how fast Jugglebot can perform some moves. So if I replace these for something faster, I think it'll perform a lot better. The second big problem with these constant force springs is that they're just not strong enough to pull the leg back down again when it's in some positions. And this leads to some really weird, janky motions happening when the platform gets too extended in one direction or another. I could, of course, replace these springs with a stronger spring, but you've got to keep in mind that because of where these springs are placed, the motor is by definition constantly fighting them. To extend the leg, the motor has to pull against all three of these springs. And if I replace them with stronger springs, then that's just more for the motor to fight. And I'll prefer to not do that to my poor little motors. My plan for what that replacement will be is essentially another string, so that when the motor spins in one direction, it will pull one string and make the leg, say, extend. And then when the motor turns in the other direction, it will pull the other string and make the leg contract. I haven't fully fleshed out this design yet, but it's very similar to what I've seen people use for their robotic arms, and I think it will work pretty well. My only real concern with that design change right now is that it would force me to change the way that I have the startup sequence work right now. With any robotic system, when you first turn it on, the motors need some way to know where they are. Generally, once they know that point, if the system is good, then from that point onwards, the system will be fine. It can keep track of where everything is, but it needs to know at the beginning where it actually is in space, because you might turn it off at the bottom, you might turn it off at the top, you might turn it off in the middle, and when you turn it back on, it's got no idea where it was before. The way that I do this right now is I make use of the fact that when the leg is fully compressed and the motor continues to turn to shorten the leg even further, the string just goes loose. And so what that means is that the motor is turning, but the leg is not moving. So I'm using the rotary encoders that are on the leg to basically say, if the motor is turning and the leg is not moving, then you're at the bottom. This will not work with my new proposed design, because when the motor turns to shorten the leg, if it keeps turning and the leg is already maximally short, it's just going to, I don't know, something will break. It's going to hit the end and the motor will stall, or the string will break, or something else will break. Maybe there's some way to do this with like some clever control algorithm, but I haven't done anything like that before, so I'm not fully banking on that working. And I'm not 100% sure what I'm going to do yet. I'll have to cross that bridge when I come to it. However, I think that's not that big of a problem because the advantage of having the strings go both ways is going to be huge. The legs should be much, much, much better at moving around. Those are the two big things that I'm planning on changing for the next iteration of Jugglebot. In my opinion, those are pretty minor things compared to what has changed recently. So I think Jugglebot is going to have this same form factor for quite a while to come. The legs will just be slightly different and the motors will be quite different. But the overall thing, I think, is going to be more or less the same. There's one more category of things that I want to talk about in this video, and that is problems and errors with this current system. The first is that the startup sequence is very janky. It's very like starty, stoppy, and it was actually so much so at the beginning when I had the acceleration set super high that a lot of the bolts in the legs actually started coming undone because they were being shaken back and forth so often. I've since lowered the acceleration way down so it's not as aggressive, but it's still a very janky, slow startup sequence. The reason for this is because when I tried making that sequence smooth, I couldn't get clean enough data from my encoders for that to work. It would work maybe 9 times out of 10, but I need this to work very reliably. How it works right now is that the stepper motor moves by a certain number of steps and then checks if the encoder has changed, and then does the same thing over and over and over again. It would be much better to do this with a time-based system. So what I'm planning on doing with the new motors is to move the motor at some slow speed for some amount of time, like 50 milliseconds, and then see if the encoder has changed. And I think by doing a time-based system rather than a step-based system, it should be much smoother. I could do that now. Like the fact that these are stepper motors doesn't preclude me from being able to do that, but I was more focused on other things. And once I got this working at all, I said, no, cool, that's done, it works. And that was the end of it. Either way, this is something that I am going to change in the nearish future. Something else that is purely an artifact of these motors being stepper motors is that there's a little bit of drift over time. If I run the same program over and over and over again, eventually the whole system starts to drift slowly. I'm pretty confident that this is because of rounding errors, and because these stepper motors can only move in integer numbers of steps, all of the math is with floating point operations. So when those get reduced down to integers, there's a little bit of rounding in there. And if you do that little bit of rounding 100 or 200 or 300 times, it starts to add up and the whole system starts to behave a little bit weirdly. There is probably some clever way for me to fix that problem in my code. There definitely is, but I'm not that worried about it because I'm going to be getting rid of these motors anyway. So that's not going to be a problem later on at all. You also might be wondering, but hang on, aren't you using these rotary encoders to check the lengths of the legs, and why don't you use that? The reason is because I'm lazy, and doing open loop control with just the numbers of steps on the stepper motor is just easier than worrying about like PID control with the rotary encoder. Once I swap these motors out for the brushless DC motors, I won't be able to use the motor cheat anymore with open loop control, so I will have to use the rotary encoders, and so I will. So again, this drift problem should, hopefully, be resolved once I change the motors out and use closed loop control and actually do this properly. The final two problems I am not too sure about. I don't really know where these are coming from, and I'm not convinced that they will be fixed once I change the motors and do closed loop control. I think they will be, but I'm not 100% sure. The first of these problems is that when the platform moves side to side, it doesn't move perfectly side to side. When it's moving in one direction, the platform will raise up a little bit, and when it's moving in the other direction, the platform will go down a little bit. I don't really know where this is coming from, and I'm not too worried about it at this point because there's a couple points where I think this could be happening. The main one is that I'm not actually telling the motor to follow a sequence of points. I'm just telling it to go from here to here. And the way that I've implemented that to get the motors to all move together is, in my opinion, a little bit sketchy. So in the future, when I move to closed loop control, and I can hopefully tell Jugglebot to follow an actual path, I think this should be fixed. Because right now I'm just saying start at point A and finish at point B. I don't care how you get there, just do it. And so I think that because I'm not giving it that information, it's not making use of it, essentially, I think. The other problem, I think, is a little bit more significant. And that is that when I tell the platform to rotate, it's not rotating about the correct axis. It should be rotating about the platform's center of mass, which is more or less where the ball is right now. But it's not. And when I tell it to rotate, it's also translating a little bit as well. I've tried checking this against my MATLAB code to see how long the legs should all be in the different orientations. And in the MATLAB code, my simulation, it works perfectly. If I just tell it to purely rotate, there is zero translation involved, as you would expect. And that tells me that the legs should be certain lengths. When I run the Arduino code, the leg lengths that it spits out are exactly the same as what the MATLAB code says they should be, but the platform doesn't move the way that the simulation moves. It translates as well as rotating, and I have no idea why this is happening. I'm not fully convinced that this is going to be fixed once I move to closed loop control. I'm just sort of like fingers crossed that it will. I don't know where the problem is. I'm not really worrying about it too much at this point because of how many changes I'm going to be making to the control of Jugglebot. So I'm just hoping that it will go away then. And if it doesn't, then I'll have to figure it out later. It's really weird. I'm not sure why that's happening. And that's it. As I said at the beginning of this video, a lot has changed since the last design. And I think it is overall way, way, way for the better. The project is looking really good. I'm very happy that it can actually finally throw. I can finally tick off the first goal for this project, to throw a ball, and I'm very, very happy about that. This project is going really well, and I am very much looking forward to seeing how it looks once I make the changes that I mentioned in this video. If you're interested in seeing any of this in a bit more detail, I'm actually going to put the CAD and the code for this on GitHub, and that'll be in a link in the description, so you can check it out if you want. I'm pretty confident that the mating and everything won't be preserved in the model, so you'll just have like one big solid model, but it should be enough for you to have a look around and you can see how all the different things work. It's also worth noting that I haven't modeled a lot of the purchased hardware on this. Like, most of the bolts are not there, the constant force springs are not there, the strings are not there. Things that I didn't really need to model just because they would be too annoying to model, I didn't include. As always, I would love to hear what you think about this, and if you have any ideas for how to address any of the problems that I have mentioned, or if you can see any problems that I haven't addressed, then please let me know. As always, I hope you enjoyed this, and I hope you have a wonderful end of the year. I will see you in 2023.